Hello and welcome to Extracting Metals by Electrolysis. Okay, so we've talked about electrolysis and the reactivity series, and this is really going to give us some context for understanding how electrolysis is done with metals. We've already talked about a couple examples, like copper, but I'm going to give you a little bit more detail specifically about aluminum and copper purification. It's really important that you take notes and memorize what's going on because aluminum and copper are always the metals that Cambridge asks about on the exam. Okay, so most metals that we use are found combined with their elements, and we talked about this, right? They're in a compound form in their ores, and these metals must be extracted before we can use them. So the method which is most appropriate depends on the reactivity of the metal. So this can be discovered using the reactivity series like we've seen. So metals that are above carbon in the reactivity series must be extracted using electrolysis. So metals that are above carbon are more reactive than carbon, and so carbon will be unable to steal that oxygen away from the compound. Okay, so they have to use electrolysis. And it's important to understand how to ascertain how reactive something is by looking at the periodic table. So when you look at a periodic table, elements are more reactive as you go to the left, and this should be easy for you to remember because and this periodic table isn't complete, but if you look at your Cambridge periodic table, the elements that are all the way to the to this side, okay, of the periodic table are the noble gases, which are the most unreactive. Okay, so as you go this way, let me pull up my pen here. Right, so we know that the noble gases are over here, and as you go this way, okay, everything gets more reactive, and also once you're on this side of the table, it's more reactive as you go down. Okay, so it's important to understand that because you have to be able to see if something is more reactive than the other. All right, so what is electrolysis? It's the process that uses electricity to separate the elements in a compound. Electrolysis is expensive because it takes a lot of energy to run the electrolytic cell, so it can only be used to extract reactive metals that cannot be extracted by other means. And aluminum is a good example of this. It's a very reactive metal that is found in the ore bauxite, okay? And it's combined with oxygen as aluminum oxide, Al2O3. So electrolysis breaks down the Al2O3 into aluminum and oxygen. And as the aluminum loses oxygen, reduction is taking place. Right? So what is the word equation for the extraction of aluminum? Aluminum oxide yields aluminum plus oxygen. Okay, so electrolysis involves breaking down ionic substances into simpler substances using electricity, and that's really the bottom line. An ionic substance, as we know, contains charged particles called ions. An ion is an atom that has gained or lost electrons, so it carries either a positive or a negative charge, which is shown after its formula. Okay, we know this. This is review for us. Ions with a positive charge have lost electrons, and ions with a negative charge have gained electrons. So in electrolysis, the ionic substance has to be dissolved in water or melted so that ions are free to move. Okay, so in electrolysis, the substance that the current passes through and splits up is called the electrolyte. And this is very important because you are going to have to label electrolytic cells and you're going to have to show where that electrolyte is. So again, this is the substance that the current passes through. It completes the circuit in the cell. The electrolyte contains positive and negative ions, okay? So what happens to these ions during electrolysis? Negative ions, so they all dissolve, okay? They're heated up, they're molten, or they're dissolved in water. It's one of those two. It's either molten, okay, or dissolved in water. Either way, those ions are moving around freely, okay? So the negative ions, we know they're going to be attracted to that positive electrode, and that's what they do. They move towards that positive electron and lose electrons. So this is oxidation, okay? Positive ions move to the negative electrode and gain electrons. Okay, this is reduction. Okay, so an easy way to remember this is the same phrase that we always use when we're talking about oxidation and reduction, which is OILRIG, right? Oxidation is loss of electrons, which means you're gaining that oxygen, right? Because if you're dealing with oxygen, then you're gaining something who hogs all of the electrons. So basically, you're just losing them. And again, if you're talking about oxygen, reduction is the gain of electrons, meaning you're losing oxygen because now you're getting back, those electrons that oxygen gains or hogs. So equations written to show what happens to electrons during oxidation and reduction are called half equations. Magnesium plus oxygen yields magnesium oxide. 2 magnesium plus O2 yields 2 MgO. Okay, so in a half equation, you have magnesium yields magnesium 2 plus 2 electrons. And we've done half equations before. Okay, so this is a reminder for you. And then in reduction, you see that it's O2 plus 4E yields 2O2 negative. Okay, and that's because magnesium is being oxidized. It's losing those electrons. Okay, and here reduction is gaining those electrons, so O2 plus 4E now has those electrons. Okay, so let's see here. Okay, so aluminum is one of the most useful metals in the world. Electrolysis is used to extract it from its core. Why isn't it possible to extract it by heating it with carbon? Aluminum ore is more reactive than carbon. Okay, it has a very high melting point. So in electrolysis, the ore is dissolved in a compound called cryolite, which effectively lowers the melting point to 1,000 degrees Celsius. So if you're looking at aluminum, it has a 2,050 degrees Celsius melting point. That is insane. It would take so much energy to melt aluminum so it would become molten so that you can separate it from its ore through electrolysis. So in order to do this, people have dissolved the ore into cryolite, and cryolite lowers the melting point. This is something you absolutely will be asked to reproduce on a Cambridge exam. Okay, so here we go. Here's the aluminum ore.
Take a look around and you'll find this wonder metal everywhere, in everything from screen doors to jet planes. Aluminum has so many applications because it's light and strong, and it's corrosion and crack resistant. Producing aluminum is costly, but it saves money over time. Aluminum, so widely used today, and the world's most abundant metallic element, does not occur in a natural state. The most available source of aluminum is actually bauxite. Bauxite is mainly mined in tropical countries. The aluminum atom in bauxite is bonded to oxygen molecules. These bonds have to be broken by electrolysis to produce pure aluminum. Bauxite is carried by rail to the plant where it will be crushed. Then, through a chemical transformation called the Bayer process, alumina is extracted. This is then roasted in calciners to eliminate all moisture. This is the reduction facility. This plant has 432 pots through which a powerful electric current will be passed to produce electrolysis. An overhead crane dumps alumina into the pots. Then the electric current from the anode passes through the alumina that we see here at the bottom of the pot. Via the process of alumina reduction at 1742 degrees, the anodes lose volume and will have to be replaced. It's a continuous operation. Each anode has a lifespan of about 20 days. Spent anodes are recovered from the pot with this overhead crane and carried off to be recycled. They clean the aluminum rods, which will then be reused. Here we see the crust formed atop the anode. When the anodes are replaced, the accumulated impurities have to be recovered from the top of the pots. This is accomplished with these pincers. Then a new anode is inserted into the alumina, and electrolysis continues. The electric current breaks the molecular bonds. The heavier aluminum collects at the bottom of the pot, while the oxygen bound to fluorine is released as a gas, which is drawn off and treated. The liquefied aluminum remains at the bottom of the pot. It has to be recovered in this huge crucible with a tube. The tube is dipped into the bottom of the pot, and a vacuum system draws the molten aluminum from the crucible. The aluminum is recovered in a short time. Air is vacuumed from the crucible by a flexible pipe held by an operator. The tube is finally withdrawn, and the overhead crane dumps another quantity of alumina into the pot. Thus, the aluminum fabrication process continues uninterrupted. The crucibles filled with molten aluminum are transported to the casting house. Their contents are poured into holding furnaces that have a capacity of 60 tons. In these very hot furnaces, the molten aluminum is stored to await casting. Finally, casting begins. The aluminum can be semi-continuously vertically cast, producing ingots, sheets, or billets, or it can be directly cast into semi-finished products. The cooling of aluminum pieces is accelerated by water sprays. The large rectangular ingots, which can weigh up to 25 tons, will head for hot rolling and eventually will be fabricated into products like aluminum foil. From 4 to 5 tons of bauxite have produced 2 tons of alumina, which in turn produces 1 ton of aluminum. This particular plant produces 200,000 tons of aluminum annually. Some other facilities can turn out as much as 400,000 tons.
Okay, so here you can see the electrolytic cell. Okay, and this one's a little bit different, so it's important to really pay attention. Let me get my pen here. Okay, so if you notice, the 2 electrodes that you have here are both anodes. Okay, they're both positive. The negative cathode is down here. And so the reason why that's done, the reason why the electrolytic cell is set up this way, is because aluminum, as you know, is a metal, and it creates positive ions. So as it's molten in this cryolite down here, as it's dissolved in this cryolite, it's these little positive aluminum charges that are being attracted to the negative cathode, right? And the positive anodes are attracting the oxygen. Okay, so oxygen is being attracted here, so you see that there would be bubbles being released, okay, from that aluminum oxide, and then the aluminum is right here, this like green layer, this darker green layer, that is being attracted to the negative cathode down here. Then the aluminum, the molten aluminum, would be removed through here, okay? So this helps to, and you can see waste gases are released here. So this is what industrial electrolysis of aluminum looks like. Okay, so looking at the redox equation, so what processes occur at the electrodes during the electrolysis of aluminum oxide? So at the negative electrode, okay, you're having the aluminum ions, which is that aluminum 3+, plus the 3 electrons, right, that is yielding aluminum, okay? And at the positive electrode, you have oxygen, okay, being removed, right? It's oxidation is occurring. So you have a negative ion of oxygen getting back those electrons to have O2, okay? O2 without it being an ion. Okay, so to do that, it's O2 plus 4 electrons, right? So remember that like if you're looking at aluminum and it's being reduced, that's gaining electrons. So when you have an aluminum that's a 3+ and you need it to be just aluminum, not its ion form, you need to do aluminum 3+ and you have to add those 3 electrons back into it, right? So it's aluminum 3+ ion plus those 3 electrons will yield aluminum. And that is being reduced, right? Because it's gaining those electrons back. And it's the same here where oxygen is being separated from aluminum. That's where the oxidation is occurring. You have an oxygen ion here. And in order for it to become not ionic form, you have to add 4 electrons to it, okay? So what is the overall equation for this extraction by electrolysis? Aluminum oxide yields aluminum plus oxygen. And you see here that's 2Al2O3, that's the aluminum oxide, and it's in its liquid form, plus 4 aluminum plus 3 O2. And you can see that aluminum is liquid, and it's being attracted to that cathode at the bottom of the electrolytic cell, and then the O2 is being released as a gas. Okay, so the economics of electrolysis. The extraction of aluminum from its ore requires large amount of energy in the form of expensive electricity to complete the many stages of the process. And you saw in that video, it's a very lengthy, large-scale process. And this energy is needed both to melt the aluminum oxide and to split up the compound. So to reduce costs, aluminum extraction plants are often located near sources of cheap electricity, like hydroelectric dams. Okay, so let's talk about copper. Copper is an excellent conductor. We use it for electricity and water pipes. It can occur as a native metal, but more often it's found combined with other elements, such as its common ore malachite. The copper extracted from compounds by reduction with carbon is impure. So remember, copper is less reactive than carbon, so it can be reduced using carbon. However, the product is not as pure as we need it to be in order to use it for electrical wires. So electrolysis can be used after reduction to improve the impurities, to remove the impurities and obtain the pure copper. Okay, so what happens at the electrodes during the purification of copper? So at the negative electrode, and remember, copper is a metal, so it makes positive ions. So at the negative electrode, you have a copper ion, so that's Cu2 plus, or 2 plus, and you need the addition of those 2 electrons to make it copper, right? Not in its ionic form. And so that's it being reduced. So there's that half equation. And at the positive electrode, you have copper in its non-ionic form being oxidized to copper 2 plus in its ionic form, plus those 2 extra electrons, okay, that it lost. So this process is carried out on a huge scale in industry, and the copper formed on the negative electrodes is 99.99% pure. And the precious metals recovered from the impurities are also sold off and help to make this industrial process profitable. All right, so here is a model for you. You can see the positive anode and the negative cathode here. The impure copper anode is placed in here. Electricity runs through. This is a copper sulfate solution. Okay, so this is how the copper is put into the electrolytic cell in a copper sulfate, right, dissolved solution. So the copper moves from the positive anode, right, because it's positively charged, it's a positive ion. It moves from that anode and it's attracted to the negative cathode. Okay, so the copper plates the cathode and the impurities sink to the bottom. Okay, that's it. Thank you for your time.